Alright, in this video we're going to look at what are known as p-series. Okay, these are series of the form where we're summing 1 over n raised to some number p, and n goes from 1 to infinity. So in expanded form, this is 1 plus 1 over 2 to the p plus 1 over 3 to the p, and so on. Alright, now question 2 on the worksheet says fill in the blanks. The p-series converges for blank and diverges for blank. So we're being asked to find the values of p that will give rise to a convergent p-series, and then to find the values of p that will give rise to a divergent p-series. Okay, now I want to start out by noting that we've already looked at two cases, right? When p is 1, we're just summing 1 over n, and that's the harmonic series, and we've shown actually in two different ways now why the harmonic series diverges. Okay, in the last video, we looked at the case when p is 2, right? We showed that the sum of 1 over n squared converges, okay? So when p is 2, we get a convergent p-series. Now up here on this number line, I'll go ahead and mark the values of p that give rise to a convergent p-series in blue, and the values of p that give rise to a divergent p-series in red. So 2 is blue and 1 is red. Alright, so next I want to point out that this series will diverge when the exponent p is less than or equal to 0. And the reason for that is the nth term, 1 over n to the p, does not approach 0 as n approaches infinity. Okay, so by the test for divergence, since a sub n is not going to 0, right, this series will diverge. Okay, now why is this true? Well, first consider the case when p is negative. Like let's say p is negative 2. Then 1 over n to the p is 1 over n to the negative second power. And that's really just n squared. And n squared does not approach 0 as n approaches infinity, right? It actually blows up. All right, what if p were equal to 0? Well, then 1 over n to the p is just equal to 1, and that, of course, does not approach 0. All right, so we get a divergent p-series when p is less than or equal to 0. And you note up here on the number line, I've shaded 0 and everything to the left in red. All right, so now let's consider the case when p is greater than 0. And we'll look at this function f of x, which is 1 over x to the p. And we note here that the function f is non-negative, okay, on the interval from 1 to infinity, and f is decreasing on this interval, and that's because this exponent p is greater than 0, okay? And so we can apply the integral test. So remember, both of these conditions on f have to be satisfied in order for us to apply the integral test. Okay, I mentioned that in the last video. In the next video, we'll look at an example where these conditions are not satisfied, and if you're not careful, you can actually arrive at a false conclusion. But here they are satisfied, so we can go ahead and consider this associated improper integral where we're integrating f of x, which is 1 over x to the p, over the interval from 1 to infinity. All right, so now if p is 1, okay, I'm integrating 1 over x, and see I highlight this case because the antiderivative here is actually a logarithm, and we already saw this when looking at the harmonic series, and we know that this, of course, is a divergent integral. Okay, now when p is not 1, I can compute the antiderivative using the power rule. Okay, so the antiderivative of 1 over x to the p, that's 1 over the quantity 1 minus p times x to the p minus 1. And here we're going to evaluate from 1 to infinity. Okay, now when I say evaluate at infinity, what I'm really saying is take the limit of this expression as x approaches infinity. Okay, now the exponent on x, this p minus 1 term, okay, this is going to play a pivotal role in determining the convergence and divergence of this integral. Okay, and I claim that when that exponent p minus 1 is greater than 0, or in other words, when p is greater than 1, this integral converges. And when this exponent p minus 1 is less than 0, so in other words, when p is less than 1, this integral diverges. And why is this true? Well, first, let's say the exponent p minus 1 is positive. Let's say it's equal to 3. Well, then I'd have 1 over x cubed, and see as I let x approach infinity, that's going to approach 0. Right? It's going to give us something finite, which implies this integral is convergent. if the exponent p minus 1 is negative, like let's say p minus 1 were negative 3, then 1 over x to the negative third, that'd be x cubed. And see, that's going to blow up as we let x approach infinity, implying that this integral is divergent. All right, so now by the integral test, since this integral here, right, it converges when p is greater than 1, that implies this associated series, this p series, is convergent when p is greater than 1. And since this integral diverges when p is less than 1, this associated p series will diverge when p is less than 1. Okay, so if we put all the above together, we get the following conclusion. The p series converges when p is greater than 1, and it diverges when p is less than or equal to 1. Okay, so you see up here, I've filled in the rest of the number lines. So 1 and to the left is all shaded red. Okay, now everything to the right of 1, not including 1, so this is an open circle there in blue. Okay, all that stuff is blue. All right, so that's going to do it for this problem. In the next video, we'll just look at a few more examples where we use the integral test. All right, thanks so much.